Hello everyone, I'm Vivekanand Talgadi, your chemistry instructor. In this particular session, we are going to take a look into the condensation polymerization. So when we speak about a condensation polymerization, actually it is a process of obtaining the polymers by condensation reactions between the monomeric unit. Okay, so naturally what happens is in this particular process, whatever the monomers that we have, okay, these monomers undergo a process of condensation in order to give rise to the polymers. But it does not only give rise to polymers over here, but along with the polymers, there are certain smaller molecules. Okay, the certain smaller molecules are usually eliminated. These smaller molecules, what are getting eliminated can be the water molecule, can be ammonia, it can be HCl, it can be alcohol, etc. Okay, so naturally, it is just like forming a polymer from a monomer due to the condensation process. Okay, now in this particular reactions, that is in the condensation polymerization, one does not require any initiators. So here, no initiators. No initiators are required. Okay, so this is our first thing that we need to remember. So in this particular polymerization reaction, no initiators are required. Secondly, what we observe is all the monomers which are involved. Okay, these monomers are usually a bifunctional. These are usually bifunctional or it can be a trifunctional. Okay, so therefore we can observe that all these particular molecules which are involved in this condensation polymerization are either bifunctional or either they are going to be the trifunctional. Now when we observe this entire mechanism, it can be explained in two different ways. The first way of explaining this particular mechanism is that let's consider as we have a monomer A. All right, so this particular monomer A, let's say that it is going to react with the another monomer that is BO here. Okay, so when this particular reaction occurs, what kind of reaction is occurring over here? And that is again a condensation polymerization. Okay, that is, it is going to condense. Monomer A is going to condense with the monomer B over here, right? So when it condenses with the monomer B, we are going to get a dimer first. Now, this particular dimer, what will happen is that it is going to react with another molecule of the monomer A. It condenses again in order to give us ABA. Okay, now this particular process as what we have, this process goes on continuing in order to give us a huge chain-like structure. Okay, and hence this particular process as what we see, it is also called as the chain growth, or you can say as the step growth polymers. Okay, so this is the way that we can explain in the first step. Now, let us take into consideration alternatively as how we can explain this mechanism. Let's say that we have a monomer A which is going to react with the monomer B. Now, when it condenses, of course, I'm going to get a dimer, and the dimer is AB. Now, this dimer AB is further going to react with another molecule of a dimer, that is AB, in order to give us AB, AB, and it goes on continuing. Correct. So if I say that this particular AB, AB, okay, is going to react with n number of the dimers, what is going to happen is we are going to end up getting over here a big chain containing continuous sequence of AB. Correct. So this is the two methods by which we can explain the mechanism of the condensation polymerization. Okay, so let's observe it in detail. So condensation polymerization or the step growth polymerization. Here, the condensation polymerization are formed by the condensation of the two or more monomer with the elimination of the simple molecules like water, ammonia, alcohol, etc. And this type generally contains the two functional group, that is the difunctional monomers. Okay, so in this process, there is no requirement for any initiator. Okay, so therefore, we can express this entire sequence in two different manners. That is, the monomers usually condense in order to give us a dimer, and this particular dimer reacts with another molecule, and it goes on increasing in every single step. Okay, that was a one way, as how we have already observed. While alternatively, this entire step growth process can also be explained by a particular monomers react in order to give us a dimer. The dimers further react with another molecule of dimer in order to give molecules of a bigger sequence. When this sequence goes on reacting with n number of those particular molecules, okay, it is going to give rise to the polymer. Okay, so this was it. Now let's observe one important example. So example that we will be taking a look over here will be of terylene or darkon. So this terylene or darkon is usually formed by ethylene glycol's reaction with terphthalic acid. Okay, now let's consider an ethylene glycol. So ethylene glycol, n number of CH2, sorry, n number of glycols, so CH2, CH2OH. So this is our ethylene glycol, right? So ethylene glycol reacts with n number of terphthalic acid. Terphthalic acid over here. So this is our terphthalic acid. Right. So now when we observe the reaction occurs in such a way that this OH and this particular hydrogen, it usually reacts in order to give rise to our product. Okay, along with the elimination of n number of water molecules. So water molecules are getting eliminated from here. So this gives rise to water molecule. So this particular section goes out. So what happens is generally this particular carbon reacts with this oxygen over here. That is, it forms the bond there. So when we observe the entire sequence, I would say that we are going to get here as CH2, CH2. Okay, connects to oxygen, C double bond O. This particular sequence continues over here in order to get attached to a benzene system, C double bond O, and this continues n times. Okay, so this particular process, as what you see, gives rise to terylene. Okay, or we can call it as a darkon. Okay, so let's observe in a very clean manner. So ethylene glycol, also called as ethene 1,2 diol, reacts with terphthalic acid in order to give us a particular terylene or darkon. Let's observe some important polyamides. Okay, so some important condensation polymers, we usually classify it under the polyamides, polyesters, and all. Okay, so for today, we are going to take a look into the polyamides first. So polyamides. Now, first we need to understand what exactly is an amide. An amide is nothing more than a molecule which contains R, C double bond O, NH2. Okay. Now, when we are speaking about the polyamides, that means these are the particular polymers which have the linkages of amides. Okay. So therefore, here these polymers have the amide linkages. That means it has C double bond O, NH. This is a linkage what is involved. Okay, so these linkages, we call them as the amide linkages. Okay, so therefore, let's observe one example in order to prove this. That is with the help of a nylon 6,6. So in nylon 6,6, what we observe is it is due to the formation, or it is due to the reaction between the two monomers. The two monomers which are involved are going to be as the n number of hexamethylene diamine. Okay, so hexamethylene. So 6 methylenes, right? So this is a hexa, 6 methylene group. Hexamethylene diamine reacts with, let's observe its a reaction with adipic acid. Adipic acid is COOH, CH2 4 times COOH. Okay, now what is going to happen here is that this H reacts with this OH. That means these are responsible for eliminating again a water molecule. Okay, so when this reaction occurs, what is going to happen is that we are going to get over here NH. This reaction happens over here also, right? So NH, CH2, 6 times NH. Okay, now the one hydrogen has been eliminated out from here, and this nitrogen gets connected to the carbon having a double bond O. This further thing gets connected to CH2 4 times C double bond O, and this sequence gets continued. That means this carbon connects to the next molecule at this particular nitrogen position, right? So now, if you observe this entire sequence, what do you see is that here is our amide linkage. If you observe this, and if you observe this, this is nothing more than a amide linkage. Okay, this particular polymer, we call it as nylon 6,6 because in this case, the first nitrogen is here. After 6 carbon, the next nitrogen comes here. Okay, naturally, again, 1 plus 4, 5, correct? 5 plus 1, 6. So this linkage goes again to the nitrogen to the next molecule. So after a gap of 6 molecules, each you would find the nitrogen systems, and hence this is called as the nylon 6,6. Okay. So let's observe preparation of nylon, and the first one is it is prepared, that nylon 6,6 is prepared by condensation polymerization of hexamethylene diamine with adipic acid under the high pressure and the high temperature. Okay, so we have this particular sequence which we have already discussed. Correct. So here is our adipic acid, and at this particular corner is our ethylene glycol. So this is ethylene glycol, and this is, of course, our adipic acid. Correct. So the reaction occurs with the elimination of n number of water molecules, right? So let's observe the next one now. Yes, its characters though, its characters and uses. The character of nylon 6,6 are these are very tough, have very high tensile strength, and they are resistant to abrasion. They are somewhat elastic in nature. Due to this, they are used in preparation of sheets, bristles for brush. They are used in textiles for making sheets. It is also blended with wool to make socks and sweaters. It is used in the manufacture of cords and climbing ropes. Okay, now when we observe about the nylon 6, the nylon 6 is actually obtained from a particular molecule, what we call it as a caprolactam. Okay, now the caprolactam is actually treated with water at the higher temperature. Now this particular caprolactam on treating with water gives a C-amino caproic acid, which is a monocarboxylic acid containing the 6 carbon atoms. Okay, so let's observe this particular process, how it looks like. Now, when I draw the diagram of this particular molecule, right. So if you observe 1, 2, 3, 4, 5, it should be 6. 6. Okay. So when we observe this entire process of using a caprolactam, let us take the caprolactam a little bit more correct in manner. So let's see. So yes, so we'll use nitrogen now. We'll place our nitrogen over here. So this is a nitrogen and this is a double bond O, right? So 1, 2, 3, 4, 5, and 6. So we have the 6 carbon systems over here. Okay, now when we have this caprolactam and this caprolactam is heated under the presence of water, what happens is this particular system is going to break down. It breaks down over at this particular position here. So as a result of which we end up getting over here NH2 connected to CH2. So how many CH2s we are going to have? 1, 2, 3, 4, 5. Okay, so we are going to have that 5 CH2s and this is connected to COOH, which is at this particular position. Okay, so this is called as the C, aminocaproic acid. Okay, so this C, aminocaproic acid, further upon heating, okay, what is going to happen now is further upon heating, it is going to form NH, CH2 5 times, C double bond O, and this sequence continues as an N number. Okay, so now this is actually nylon 6. Okay, so this particular process continues along with the elimination now of a water molecule. So this is all about the nylon 6. Okay, so we have represented over here in a perfect manner. So this particular nylon 6 is used in the preparation or the manufacture of the tire cords, fabrics, and ropes. Now, let's go with the next section, and that is going to be the polyesters. So when we observe about the polyesters here, okay, now esters, first we'll understand the esters. See, ester is nothing more than a molecule which has an RCOOR. This is an ester. Okay, if you observe, if you open the structure, it is going to be as RC double bond OOR. Okay, these are the esters. So now, polyesters, that means a particular polymer which contains an ester linkage. Ester linkage is C double bond O, and this particular section continues N times. So this particular linkage, we call it as a polyester. Okay, so molecule or a polymer containing these particular linkages, we call them as the polyesters, and this linkage over here, we call it as an ester linkage. Okay, now we shall observe certain examples. So here in this case, so the first example, of course, again comes back to the terylene, that is the reaction of ethylene glycol and terethylenic acid, also called as the dark one, which we have already completed this in our first session itself for today. So here, what is happening? N number of ethylene glycol reacts with N number of terethylenic acid. Correct. So here, the ethylene glycol is reacting with N number of terethylenic acid. The reaction occurs at this particular position, and therefore it forms the bond. That is, this particular carbon forms the bond with this oxygen over here, and that is can be observed here. And when the reaction occurs, it ends up eliminating N number of water molecule, and this is our dark bond. Correct. Now let's observe the uses of dark bond. So it is used for mixing with cloth. Okay, so it is used in preparation of your clothes by mixing it with the cottons. It is used in the seat belts and sails. It is used in the preparation of films, magnetic ropes, magnetic tapes, packing for the frozen foods, etc. Correct. Now, it is used as a good substitute for the human blood vessels in the heart bypass operations. Now, coming towards the next type, and that is called as the phenol formaldehyde polymer. So, phenyl formaldehyde polymer is a polymer which is obtained by the reaction of the phenol and formaldehyde. Okay, now let's observe this. When you observe the reaction that is of the between the phenol, okay, so this is a phenol. So here, the phenol reacts with formaldehyde. Okay, so formaldehyde HCHO, right? Now this particular reaction can either takes place in an acidic condition or a basic condition where acids and bases are acting as a catalyst. So here the catalyst is required. So the catalyst can be an acid or it can be a base, right? Now when this reaction occurs, we are going to get over here the mixture of the ortho and the para products. What are the products that we are going to have? Now these products are going to be as benzene system. Along with the benzene system here, we are going to have OH, CH2OH. Okay, so this is our ortho product, right? So plus we can have over here another molecule. Please observe now carefully. Here again CH2OH, along with over here CH2OH plus another molecule OH, CH2OH, here again CH2OH, and here again CH2OH. Okay, so these are a mixture of our ortho and para products. Okay, now what happens is that when we take these and when we heat it further, okay, now due to heating, what is going to happen is it is going to give us compounds wherein the cyclic systems are attached. Okay, now these cyclic systems are attached by the help of CH2 bonds. So it looks something like this upon further heating. So after further heating, this system over here, CH2, here we have an OH, here we have CH2, this connects further to another benzene system, this gets connected to OH, CH2, here it again gets connected to OH, here it gets connected to CH2, and this particular system goes on continuing like these. Okay, now this is what we call it as novolac. Okay, now this novolac is usually used in paints and varnishes. Okay, so this huge chain like structure, we call it as novolac, right? Now, let's observe this in a correct manner. So these particular formaldehydes, that is a phenyl formaldehyde polymer, are obtained by the reaction of the phenol and formaldehyde under the presence of either an acid or a base. We have already spoken about this. These are used as a catalyst. Okay, now the reaction starts with initial formation of the ortho and para hydroxymethyl phenol derivatives. Okay, we have seen 3 derivatives, correct? Further, which reacts in order to give a linear polymer wherein the compounds contain the chain-like system, the ring-like systems connected to each other by the help of a CH2. Okay, now as I said that these particular linear product novolac is used in the paint. Now further, if we heat this novolac, what is going to happen is it will give rise to an unfusible mass. That unfusible mass, okay, because of the extensive cross-linkings, and this is how it looks like. Okay, so this is about the bakelite. Now, bakelite can be obtained in 2 different ways. The 2 different ways, that means it can be either a soft bakelite, wherein the cross-linkings are less, or a hard type of bakelite. If these cross-linkings that you see, if these cross-linkings are less, then we get a soft type of bakelite, and if these particular cross-linkings are extensive, we will end up getting over here a hard type of bakelite. Okay, so we have those two types. So soft bakelite is used in as a glue for the laminated wooden planks. Okay, so these are soft bakelites in a sense. This is a bakelite with lower degree of polymerization, right? While the higher degree of polymerized bakelite is used for making combs, phonographs, records, electrical switches, and handles of various utensils. Okay, so let's go with the last case, and the last case that we need to discuss now is going to be the melamine formaldehyde polymer. So when I'm speaking about the melamine here, okay, so the melamine is nothing more than a particular aromatic systems which contain NH2. Okay, it is connected to N. So this we have here as N. Here we have a NH2. Double bond N connects over here again NH2, and this system continues, right? Plus HCHO, that is a formaldehyde because it is reacting with a formaldehyde, right? So here we have formaldehyde. So when this particular system reacts, what we'll have is first it gives rise to an intermediate, what we call it as a resin intermediate. Okay, so the resin intermediate is formed because of the reaction between the amine group and the formaldehyde. So as a result of which we end up getting over here NH2, double bond N, single bond over here, and here a double bond, and here comes is the NH, CH2OH. Now this is actually a resin intermediate. Okay, now this resin intermediate is what we have. This further reacts in order to give an entire big polymer, an H, double bond N, NH, this particular system goes continuing over here. This is a double bond that what we have here, N, NH, CH2, and this system continues. Okay, so this is called as a melamine polymer. Okay, now this particular melamine polymer is usually used in preparation of the unbreakable crockeries such as the cooking utensils, etc., like cups, vessels, and all. Okay, so it is formed by the condensation of the melamine with formaldehyde. So we have a melamine over here. The melamine is reacting with the formaldehyde, right? So in our first case, as I said, we are going to get a resin intermediate, which we have already seen. This resin intermediate further polymerizes in order to give a perfect melamine polymer. And of course, it is used in preparation of the hard and unbreakable crockery items like the cups, plates, utensils, etc. Correct. So here we are going to end up with this particular session. Thank you and do take care.